Hello everyone, my name is Shrutika Sarave and I am currently a third year student of Computer Science and Engineering. As a part of internship at MSc Information Technologies, I have had the opportunity to work on an embedded system project. This internship has provided me with a valuable hands-on experience in embedded system where I have been able to apply theoretical concepts to a real world project. In this presentation, I will be sharing the objectives of the microwave simulation, the technologies and tools I have used, as well as the insight and challenges I encountered during this process. Goal of internship to learn about C language and embedded C programming, to learn about the microprocessors and microcontroller, to learn and implement the project of microwave oven simulation on PIC microcontroller. Table of contents, introduction, installation of required tools, topic learned during the internship, embedded systems, microcontroller and microprocessor, PixSimLab compiler and MPLab, CLCD tactile switches, matrix, keypad, interrupt, ISR, timers, conclusion, and last is project demo. Introduction. Microwave oven is used to heat the food and for the cooking purpose. Using microwaves, which is of the form of electromagnetic waves. There are several modes in the various microwave ovens. Here we are going to implement four cooking modes. First, microwave mode, grill mode, convection mode, and start mode. Installation of required tools. To begin the internship, several essential software tools had to be installed, including MPLab IDE, a platform for coding and debugging microcontroller programs. The XC8 compiler was used for programming specific to microcontrollers, while PixSimLab provided a simulation environment to test code and circuits before implementation. These tools allowed for seamless development and debugging of embedded system projects. Topics learned during the internship. The internship covered various important embedded systems topics. Key areas included understanding the difference between microcontrollers and microprocessors, learning the program with X8 compiler and simulating circuits with PixSimLab. We also explored hardware components like CLCDs, tactile switches, and matrix keypad for user interaction. Concepts, concepts like interrupts, ISRs, and timers were learned to handle real-time processing in embedded application, providing a comprehensive foundation in embedded system development. The next is embedded system. An embedded system is a specialized computing system designed for a specific function within a larger system. Unlike general purpose computers, embedded systems are optimized for dedicated tasks, often with constraints on processing power, memory, and energy usage. Examples include control systems in automobiles, medical devices, and consumer electronics. Learning embedded system in the internship involved understanding how the systems are designed, programmed, and interacted with hardware. Microcontroller and microprocessors. Microcontrollers are compact devices that combine the microprocessor, memory, and input or output peripherals into the package designed for embedded application. They are low power and cost effective, making them ideal for control systems. Microprocessors, on the other hand, are typically more powerful processors used in general purpose computing. While microcontrollers are used for specific repetitive tasks, microprocessors are designed for more complex and versatile operations in devices like computers and smartphones. PiximLab, XC8 compiler, and MPLab XIDE. PiximLab X8 the internship involved using PiximLab for simulating PIC microcontroller circuits and programs, providing an environment to test code implementation. The XC8 compiler was used for writing C code for PSC microcontroller, converting into machine readable instruction. The MPLAB IDE was the integrated development environment where coding, debugging, and simulation occur. These tools together streamline the development process, allowing for efficient programming and testing of embedded systems. Next is CLCD tactile switches and matrix keypad. CLCD tactile switches. In embedded system, a CLCD is a character LCD is used to display text and data. During the internship, we learn how to interface the CLCDs with microcontrollers to display information. Tactile switches were also explored as a form of user input. These simple switches allow users to trigger specific actions, such as changing settings or controlling devices by pressing them. Interfacing both of these components enable the interaction of interactive embedded system. Matrix keypad. A matrix keypad is a device used to detect multiple user inputs using fewer pins by organizing the keys in rows and columns. During the internship, I've learned how to interface a matrix keypad with a microcontroller. When a key is pressed, the intersection of the corresponding row and column is detected, sending an input signal to the microcontroller. This efficient method is commonly used in devices like security systems, control panels, and digital clocks. The next is interrupt and ISR. Interrupt An interrupt is a mechanism in a embedded system that allows the microprocessor to respond immediately to an external event, pausing its current task. Interrupts are the crucial for handling real-time events such as sensors, inputs, or communication signals without needing to constantly check for them. During the internship, we learned how to configure and manage interrupts in the microcontroller, which enabled us to design systems that can react instantly to critical events or inputs, improving efficiency. ISR, Interrupt Service Routine. An interrupt service routine is a special function that is executed when an interrupt occurs. The ISR temporarily halts the main program, executes the required action, such as processing data or handling input, and then resumes the main program. We have learned to write the ISR during the internship to handle specific interrupts efficiently, allowing our embedded system to react to external stimuli like button presses, sensor readings, or timers, enhancing real time processing capabilities. The next is timers. Timers in embedded systems are used to measure time intervals, generate delays, or create periodic events during the internship. We explored how to configure and use timers in microcontrollers. Timers allow for precise control over events, such as triggering an action after a delay or counting pulse from sensors. They are essentially for tasks like controlling the timing of operations, creating delays, or generating regular interrupts, helping manage the time sensitive nature for embedded system. This is the block diagram for microwave oven, which shows the various components of microwave oven. In conclusion, the internship provided valuable insights into embedded system and hands-on experience with key tools and concept. The final project demonstrated how to integrate knowledge of microcontrollers, hardware interfacing, and real-time programming to create functional embedded system. The project not only reinforced the theoretical concept but also allowed for practical application, helping me develop problem-solving skills in embedded system design, programming, and debugging. The internship was an enriching experience, preparing me for future challenges in the field of embedded system. Let's see the project demo. For successful execution, we have to build this code. It will show the code is executed successfully. Now we have to load this in PiximLab by the reload option. Reload last. It will display microwave oven, powering on microwave oven, and the cooking modes: micro mode, grill mode, convection mode, and the start mode. By pressing 1K, microwave will start, and it will display power. Then we have to set time for micro mode. We will set 30 seconds. By pressing star K, it will be clear. And by pressing hash K, the process will start. The fan will show the microwave is working. By pressing 4, we can start or resume it. It will show the start and resume of process. After timer, the buzzer will be on. It indicates the work is done. For grill mode, we have to press second key. We have to set time for it. By pressing hash, the process will get on. The buzzer will be now on after timer. Third is convection mode. We have to press 3 for it. For convection mode, we have to set temperature. This is the preheating time. Which is 3 minutes. After the preheating completed, we have to set time for cooking. And pressing hash, the process will on, and the fan indicates the process. After time up, the buzzer will get on. By pressing 4K, the process will again start. Again by pressing 4, we can resume the process, and by pressing 5 we can pause it, and by pressing 6 we can stop the process. By stopping it, fan will also stop. It shows the process is stop. This is all about project demonstration of microwave oven simulation. Thank you.